Chain rule for sine and cosine functions. So if when we create a composite function, the outside function is either a sine or a cosine function, we can approach the chain rule using the same types of substitutions that we've been using for the previous sections. So here, consider the function y equals sine of x cubed plus e to the x. We can rewrite this as y equals sine z, where z equals x cubed plus e to the x. So notice again that our z is the inside function from the original composite function. If we want to find the derivative dy dx, we can find the derivatives dy dz and dz dx and multiply them together to get the derivative that we want. So let's take a look at those. So let's start with dy dz. So dy dz, we're going to come over here to the function that has y and z in it, which is sine z. The derivative of sine is cosine. So we get cosine of z. Now dz dx, our second derivative that we need, we're coming over here to the formula that has z and x in it. And when we take the derivative of that function, we get 3x squared plus e to the x. So these derivatives all come from our basics chart. Now, when we multiply these two derivatives together, that's how we get the derivative we want, dy dx. So that means we're going to have cosine of z times 3x squared plus e to the x. Now I'm using parentheses around my second term because there's more than one term there. And whenever there's more than one term, I need to use parentheses to indicate that it's multiplying both terms. So that cosine multiplies the entire derivative, not just the first term. Now remember, I don't want z's in my final answer. So one more step I need to take is I need to substitute back in what z equals so that everything is in terms of x. So my z equaled x cubed plus e to the x, so I substitute that back in, times 3x squared plus e to the x. Now I want you to notice that the original function was sine of x cubed plus e to the x. In our derivative, we have cosine of x cubed plus e to the x. So that means that whatever is inside the argument of the trigonometric function, it doesn't change within the trigonometric function. Just the outside part changed. Sine changed to cosine. And then we had to multiply by something extra, which was the derivative of the inside. Let's look at another. Example 1. Find the derivative of y equals f of x equals cosine of x to the sixth. So I want to start by identifying my inside function. So my inside function is going to be x to the sixth here. Again, it's the function inside my trigonometric function. I'm going to need the derivative of that as part of my overall derivative process. So the derivative of x to the sixth is 6x to the fifth. Additionally, I want to rewrite my original function with a z in it. So here, instead of cosine of x to the sixth, I have cosine of z. I also need dy dz, the derivative of y with respect to z. The derivative of cosine is negative sine. So now, to get dy dx, the derivative I want, I can multiply the two derivatives that I had that comprised in the chain rule. So I have 6x to the fifth times negative sine z. So a couple things here. I don't want a z in my final answer, so I'm going to need to substitute back in. Additionally, I have a negative sign, and normally I'm going to pull that negative sign out to the front. So now I'm going to have that my derivative is negative 6x to the fifth. So again, I moved the negative to the front, times sine, and instead of z, I'm going to have x to the sixth. So my derivative is negative 6x to the fifth times sine of x to the sixth. Again, the original function was cosine of x to the sixth, and in my derivative, I have a sine of x to the sixth, again reinforcing the idea that whatever's in the argument of the trig function doesn't change. What changes is the outside part of the trig function, and then we multiply that by the derivative of the inside. So now let's look at a shortcut of how we can write these differentiable functions. If z is a differentiable function of x, then the derivative with respect to x of sine of z is cosine of z times dz dx. Similarly, if the derivative with respect to x of cosine of z is going to be equal to negative sine of z times dz dx. So as long as we can identify what our z is, we can use these formulas to make our calculations a little more efficient. Let's look at an example. Find the derivative of y equals sine of 4x to the fourth plus x squared. So here, I need to figure out what my z is, my inside function from my composite function. So here, my z is 4x to the fourth plus x squared. So my shortcut formula for sine, that's the one on the top, says that my derivative is going to be cosine of z, which is 4x to the fourth plus x squared, times dz dx. So I need to take the derivative of z with respect to x. So here my derivative will be 16x cubed plus 2x. Notice I have more than one term, so when I put it as part of my derivative, I'm going to use parentheses. So 16x cubed plus 2x. So it's these two things multiplied together that's going to comprise the derivative of my function. I want to also point out that I cannot multiply the functions that are inside the cosine argument with the function that is multiplied outside the cosine argument. The things inside the cosine argument need to stay there and together. So I'm not going to be doing any combining here. My final answer is going to stay just like this. Let's look at another. Example 3. Find the derivative of y equals cosine of the natural log of x. My first step again is going to be to identify the inside function. Here, my inside function from my composite function is the natural log of x. So once I have my z, I can go ahead and use my formula. My formula says that the derivative of cosine of z is going to be negative sine of z, which is the natural log of x, times dz dx. So I need to find the derivative of this function. The derivative of the natural log is 1 over x. So this is going to be multiplied by 1 over x. So again, I'm not going to do any further simplification here. I cannot multiply the 1 over x into the sine function. Whatever's inside stays inside and nothing else gets added in. And the negative is already in the front. So here my final answer is negative sine of the natural log of x times 1 over x. Let's try one last problem. Example 4. We're going to revisit a problem we did earlier, but we're going to look for different information. So during one particular day, the value of a stock, V of T, for Math Incorporated, opened at $45 a share at 9 a.m. and closed at $45 a share at 5 p.m. It varied periodically during the day, with time t in hours since 9 a.m., and can be modeled by V equals 38 sine of pi over 4t plus 45. We want to find the rate at which the value of the stock is changing at 1 p.m. So the rate at which the value is changing, that means we want to find the derivative. And not only do we want to find the derivative, we want to find it at 1 p.m. Now remember, time is hours since 9 a.m. So since we're measuring hours since 9 a.m., then 1 p.m. means that time equals 4, since 1 p.m. is 4 hours after 9 a.m. So once we find our derivative, we need to plug in a 4. So looking at our derivative here, we can see that we're going to need to use a chain rule because we don't just have a sine of t, we have a sine of pi over 4t. So here, let's just rewrite our function. V of t equals 38 sine pi over 4t plus 45. So in terms of my composite function, my z is pi over 4 times t. So that's what's on the inside of sine. If it's anything more complicated than a single variable, we need to be using the chain rule. So that means I'm going to also need dz dt, the derivative of z with respect to t, to multiply for my shortcut. So pi over 4 is a constant. If you have a constant times t, the derivative is just that constant. So dz dt is pi over 4. So now, to get my derivative, I have to use a couple rules. The first is the constant multiple rule. So the 38 is going to carry. The derivative of sine z is cosine of z, where my z is pi over 4 times t, times dz dt, which is pi over 4. And then I go to my next term. So these two terms are separated by addition or subtraction, addition in this case. And so I treat the 45 separately. The 45 is a constant, so when I take the derivative, I just get 0. So remember, I'm looking for my first derivative at 4. So I'm going to plug in a 4 for t. So I have cosine pi over 4 times 4, all times pi over 4. When I crunch that number in my calculator, I'm going to get negative 29.85. So let's remember what the units are here. So V is the value of the stock in dollars. That's my dependent units. So that's going to be what's on top, so dollars. And then my time units are going to be my independent variable, and that's in hours. So that means that my stock is falling, right? It's decreasing because my derivative is negative. And so at 1 p.m., the value of the stock is falling by $29.85 for each additional hour that I go on. So if I go from 1 o'clock to 2 o'clock, I expect the value to fall by $29.85.